Welcome to the Blodgett Hydrovection HV-100E wiring diagram review. The Hydrovection has a 3-page wiring diagram. We will be looking at a 480 volt unit today. Let's start on page 2 at TB1 or terminal block 1. This is our field connection for the supplied unit voltage. Notice the 480 volt power is indicated by red at L1, green at L2, and light green at L3. We see L1 and L2 going to the fuse holder that contains 2 fuses. The fuses pass L1 and L2 power to our step-down transformer. The step-down transformer sends 208 volts, shown here as violet and blue, to CB1. CB1 is our circuit breaker located on the front control panel of the unit. It sends 208 volts to TB2. Terminal block 2 is our 208 volt distribution point within the unit. It sends its 208 volts to the AC 24 volt transformer, the motor inverter, and the 24 volt DC power supply. The AC transformer takes the 208 volts and translates it into 24 volts AC. It sends this voltage to the control board and the I/O or relay board. This voltage is indicated by the tan and light blue lines. The 24 volt DC power supply sends 24 volts DC to terminal block 4 and terminal block 3. This voltage is indicated by the pink and gold wires. Terminal block 3 supplies DC 24 volts to the door switch and the cavity high limit. When the unit calls for lights, the relay board sends a 24 volt DC signal through terminal block 3 to the light circuit. Inside the unit, to the left of the elements, there's a capillary that locates back to the cavity high limit. The cavity high limit takes a 24 volt DC signal to its normally open contacts. If the cavity high limit closes, it sends 24 volts back to the relay board to trigger a high temp error, and it also activates the shunt trip coil of CB2, which disables the 480 volt output to the contactor. Circuit breaker 2 supplies voltage in 480 volts to the contactor. K1, or the heat contactor, is triggered by 24 volts DC from the relay board whenever a call for heat is present. When the K1 coil is active, it sends 480 volt power to the elements. The elements remain on until the 24 volt DC signal is removed from the contactor. Next, we see the 24 volt DC return signal present at the motor inverter and the fan's normally closed thermal switch. The normally closed switch sends that signal back to the motor inverter drive to terminal 5. Now we see a call for fan from the unit's relay board, which triggers the motor inverter to send three-phase power to the motor. Whenever the signal is present from the relay board to the motor inverter drive, the drive at set speed signal is sent back to the relay board. If the output signal is present, but the return drive at set speed signal is not present, the control will trigger a fan error. Also notice that the fuse holder and the step-down transformer are exclusive to the 480 volt unit. These two items would not be present in a 208 or 240 volt unit. Now let's look at page 1 of the wiring diagram, starting at TB4. Terminal block 4 has 24 volt DC power supply. It distributes this power to the location shown here. Now we see the front control panel. Front controller is supplied by 24 volt AC power. Also, the front controller has a USB cable that runs to the front control panel of the unit. Here we see the harness connecting to the 3-button auxiliary board located above the control. And finally, we see the COM or communications cable that enables communication between the front control and the relay board. Now we see the door switch. It's supplied by 24 volt DC power. When the door switch is closed by closing the door, that 24 volt DC power is sent to the door close signal at the relay board. At the relay board, we see it's supplied by 24 volt AC power. Here we see the COM cable and its other end. When the high limit is tripped, we notice the 24 volt input signal sent to the relay board that would trigger the high limit error. Next, let's look at the 4 outputs that enable a call for the fan. When the outputs are present, calling for a fan, the relay board looks for a signal return from the drive at set speed signal output from the motor inverter. If this were not present, it would trigger a fan error. When the relay board is instructed to call for interior cavity lights, the 24 volt DC output signal shown here would be present. For a call for heat to be successfully initiated, first the power button must be on the front control. Then the drive at set speed signal must be returning to the drive at set speed input at the relay board. And with these two conditions met, and a call for heat present, the contactor outputs will be enabled. Here we see the leads running out to the 4 unit probes. Let's take a closer look at those probes. First, we have the cavity probe. This is located inside the oven cavity, and it controls the call for heat. Next, we have the inverter probe. This is located directly below the motor inverter, and this probe controls the axial cooling fan and the control compartment of the unit. Next, we have the quench probe, located in the rear of the unit at the quench box. This probe is used to control the drain temperature of the unit. And finally, we see the product probe. This probe is used to control the oven's operation by the temperature of the product inside the oven. Now we see the solenoid manifold. First, the 24-volt signal being sent to the spritzer solenoid would enable water into the oven cavity. Now we see the 24-volt signal being sent to the quench solenoid that would enable the cooling of the drain. Here we see the vent solenoid. This vent solenoid opens and closes a vent located at the rear of the unit. And here we see the axial cooling fan. This fan cools the control compartment of the unit. Finally, let's look at the third page of the wiring diagram. This page shows us the 3-button auxiliary board. It's supplied by 5 volts DC from the controller. When a button is activated, the returns go back to the controller as shown here. This concludes our review of the 3-page wiring diagram for the hydrovection oven.